Okay, good morning. Good morning. So, in the last lecture we started discussing about the semantics, and our goal was to find suitable domains. So in the semantics what we do is we try to define denotational semantics. So what we want to do is we want to define a function val which tells us for every Haskell expression what the value is. So it should be a function from Haskell expressions to objects of some domain, and the question is, first of all, how does this domain look like? And at the beginning we only wanted to look at monomorphic types, so no polymorphism, no type variables. And then for every type we want to have a domain where we have corresponding objects. And so at the moment for every type, for every Haskell type, tau, we need a corresponding domain. Domain which I called dom tau. And now how does this domain look like? Well, for the predefined simple data structures like integers, booleans, characters, floating point numbers, it is rather easy. So here, for integers, for example, we use this domain up there, z bottom. Z are the integer numbers, and there is one additional element bottom which denotes undefined. And we proceed similarly for booleans and for characters and for floating point numbers. And now the problem is we have some objects which are defined and some objects which are undefined, and some of them are not completely undefined but only partially undefined. And so in order to compare these objects we need a relation. So compare objects of such domains. So of a domain D, we compare the objects by a relation, and this relation was a reflexive order or ordering. Sometimes we write order, sometimes we write ordering, that's the same. So by a reflexive order, which we denote by the square subset equal sign. So this means an object which stands here is less defined or equal than an object which stands here. Now, for those very simple domains, they are flat domains. And flat means we either have something which is completely undefined or else everything is completely defined. So bottom is less defined or equal than 0. It is less defined or equal than 1, less defined or equal than 2, and so on. But these numbers up here are incomparable. They are all completely defined, and so we don't have that 0 is less defined or equal to 1. And similarly, 1 is also not less defined or equal than 0. Now for tuple types, it's a bit more interesting here. For the tuples of integer numbers, we would build domains which look similar to this one. Not exactly like this, but similar to this one. So whenever we have two domains, we can build a cross product, and then we have, again, a new domain. And we can not only do this with two domains, but also with 3 or 4 or n. And then this relation, less defined or equal, is defined component-wise. So a tuple d1 to dn is less defined or equal than a tuple d1 prime to dn prime, if and only if each component, so d1 is less defined or equal than d1 prime, d2 is less defined or equal than d2 prime, and so on. So, for example, the tuple bottom bottom is less defined or equal than the tuple 0 bottom, and this in turn is less defined or equal than the tuple 0 0. So now we have some objects which are, like this one, which are not completely defined, but also not completely undefined. So now we have chains where objects increase in their definedness, and these chains can have more than just length 2. And for functions, it's even more interesting now. Well, if we have a function from z bottom to z bottom, so functions on domains, we can again compare them by their definedness, and that's defined argument-wise. So a function f is less defined or equal than a function g, if and only if this holds for all the values on all arguments. So for all arguments d, f of d has to be less defined or equal than g of d. Okay, so this is what we defined. Now, since we look at these strange sets where we have this bottom element, we normally have to extend functions that we already know on the integers, for example, to these new domains which contain this bottom element. And then the question is, how do we do this? And one option is that we say, well, whenever one of the arguments is bottom, so whenever one of the arguments is undefined, the result should also be undefined. If we do this kind of extension, then the function is called strict. So a strict function is a function where whenever an argument is undefined, then the result is undefined as well. Now, let's look at an example. This was the example we had at the end of the last lecture. This is the function, this is Haskell. So this is the Haskell function 1, which is defined like this. 1 of x is 1. And now the question is, what should be the semantics of this function? And I made 3 suggestions, and we have seen that this suggestion, I mean, for integer numbers, this has to be a function which always returns 1. The only interesting question is what happens if the argument is undefined. Now, if we want a strict function, then a strict function has to be undefined whenever the argument is undefined. So then we would have to choose f2. So f2 would be 1 for integers and would be bottom if the argument is bottom. And in a strict functional language, this would be the semantics of 1. Now in Haskell, which has non-strict semantics, which has outermost evaluation, we would choose f1 as the semantics. So here, for integers, the value would be 1, and for bottom, the value would be 1 as well. Because in Haskell, you would evaluate from the outside, and you can see that you don't need to evaluate the argument in order to determine the value of 1. And of course, there are some other possibilities. For example, f3. Now, f3 would give 1 if the argument is defined, if the argument is an integer, and it would give 0 if the argument is undefined. And now this function solves the halting problem, because what this function does is it first looks at its argument and finds out whether its argument is defined. And then afterwards it returns 1 or 0 depending on whether the argument is defined or not. And it is well known that the halting problem is not computable. So this function is not computable. You can't write an algorithm which computes this function. And in general, this is true whenever you have the following property. So in general, functions f with f bottom is not bottom. So if they are applied to something undefined, they give you something that is defined. But for some other object, they give you something different. So if you have a function which, for some argument, it returns you something which is different from what it returns at point bottom, such functions are never computable. And the reason is, such a function would have to look at its argument and find out whether its argument is defined or not. If it's defined, and if it's D, f has to return something different than if it's bottom. And if it's bottom, it still has to return something that is defined. So these functions are never computable, and therefore we don't want functions like this in our semantics. So it can never happen that a Haskell function has a function like this as its semantics. And therefore, we restrict the set of those functions that can be used in the definition of the semantics. And exclude such so-called non-monotonic functions which are not computable. I mean, we are interested in defining the semantics of a programming language, so clearly we only need to have computable functions. So what do I mean by monotonic? Monotonic means the following. So this is the definition of monotonic functions. And monotonic more or less means the same as it usually means, but for the special case where we have this less defined or equal relation. So if we have two orderings, two partial orderings, D1 and D2, let these be orderings or orders on D1 and D2 respectively. And then we say a function f from D1 to D2 is monotonic if the following holds. If D is less than or equal to D prime, then f of D also has to be less than or equal to f of D prime. So this must imply f of D less than or equal to f of D prime. So in other words, if the argument gets more defined, then the result of the function also gets more defined. If the argument becomes more defined, then the result of f also becomes more defined. And you can see that if we look at our three functions f1, f2, f3 here, f1 is monotonic. So bottom is less than or equal to every integer, and the argument and the result is 1, and 1 is less than defined to 1. So this is monotonic. f2 is also monotonic. Bottom is less defined or equal to x for all integers x, and the result of the function indeed becomes more defined. Here we have bottom, there we have 1, and bottom is less defined or equal than 1. But f3 is not monotonic. Here, again, bottom is less defined or equal to x, but 0 is not less defined or equal than 1. So here, if you make the argument more defined, then the result suddenly changes completely. It's not that just the result becomes more defined, but the result was already completely defined, and now it changes from 0 to 1. So that's not monotonic. And indeed, all computable functions are monotonic. So if we exclude the non-monotonic functions, we only exclude functions that can never occur in the semantics. So all computable functions are monotonic. Now the converse is not true. There are monotonic functions that are not computable, and we will see such functions later on. Okay, let's look at one more example. And the example is the identity function on integers. If I write it down in Haskell, it looks like this. It goes from int to int, and it of x is x. Now, what should be the semantics? What should be the semantics of it? Now, it should be a function f. And now on integers, it's rather clear what it should do. It should give us x for all integers x. And what should happen on bottom? Now, what is your proposal? The semantics. I mean, there are many possibilities. 0, 1, 2, minus 1, minus 2. Bottom. And why does it have to be bottom? If it's not bottom, then it's not computable. The problem is if you say f of bottom is 0, then f of bottom is 0, but f of 1 is 1. Bottom is less defined than 1, but 0 is not less defined than 1. So otherwise it's not monotonic. So otherwise it is not monotonic and therefore not computable. Therefore not computable. So we can see immediately that in contrast to 1, here the semantics is a strict function. Now there is no other choice. For 1, there are two possibilities, A or B, and in Haskell we want to take A, in other languages we would take B, but for this function there is no choice. For this function, this is the only possible semantics also in Haskell. So here f is strict, because if the argument is undefined, then the result is also undefined. Now, and indeed, every strict function is monotonic. And this can be formulated as a lemma. So here's the lemma. And this is lemma 218. And the lemma basically says strictness implies monotonicity. But this is only true for flat domains. So if we have domains d1 to dn and another domain d, let these be domains where d1 to dn are flat. So they look like these base domains where we have one bottom element and everything else is defined. So they are flat. Now if we have a strict function f which goes from d1 cross dn to d, and this should be strict, and strict means whenever one of these arguments is bottom, then the result is also bottom, then f is monotonic. Okay, and let's try to prove something like this. So these proofs are not very difficult. Okay, what does it mean to be monotonic? Monotonic means, let's take two elements, two arguments. If the one argument is less defined than the other, then similarly the result should be less defined for the first argument than the result for the second argument. So, okay, let's say the first argument is d1 to dn. It's the first tuple, and this should be less defined or equal to d1 prime, dn prime. Now I omit this index whenever it's clear from the context. So this is the less defined or equal relation on capital D1 cross capital D2 cross and so on capital Dn. So what we have to show is, we have to show that then f of d1 to dn is less defined or equal than f of d1 prime to dn prime. Okay, there are two possibilities. Case one is they are equal. So if they are equal, then we clearly have what we want. I mean, if d1 to dn is equal to d1 prime to dn prime, then if we apply f, we still get the same result. So this is the trivial case. The other case is the otherwise case. So now they are not equal. Now if they are not equal, I mean this here means that D1 is less defined or equal than D1 prime, D2 is less defined or equal than D2 prime, and so on. And if they are not equal, then there is some di where di is different from di prime. So there is some di which is different from di prime. For some I. And then therefore, since we know that this is defined component-wise, we know that di is less defined or equal than di prime. Now if di is less defined or equal than di prime, and if they are not equal, and we are in a flat domain, then we know how di looks like. Since we have this, and since we know that di is flat, what can we conclude from this? So flat means something is either defined or it's bottom. Mm-hmm. Then di is bottom. That's the only solution. Di is bottom and di prime is not bottom. Otherwise, we cannot have that one thing is less defined, strictly less defined than di prime. Now, what do we know? Now we know that f is strict. Then f of d1, somewhere here we have this di, and this here is bottom. Now if f is strict and we apply it to arguments where one of the arguments is bottom, strictness means if one of the arguments is bottom, then the result is also bottom. Now on bottom is clearly smaller or equal than anything else. And this is what we wanted to show. So f of d1 to dn is less defined or equal than f of d1 prime to dn prime. So indeed, in this case, strictness implies monotonicity. Now, as I said, we are only interested in computable functions, and therefore we are only interested in monotonic functions. But strict functions is a bit too restrictive. I mean, clearly, we need functions in our semantics which are non-strict. And here we have an example. So if we would have a programming language like Lisp or ML, then we could say, okay, we restrict ourselves to strict functions. But if we have Haskell, we can't do this. So since Haskell uses lazy evaluation, we also need non-strict but monotonic functions in our semantics. And this F3 was an example. Yeah, F3 is not computable. F1 is the one that we use in our semantics. So an example was the semantics of this function 1 that we have on the slide over there. Okay, so now the question is, okay, we now know that we will only look at monotonic functions. We will later on see that this is still too much. We will restrict ourselves a bit further later on. But then still the question is, how can we now find the semantics? I mean, for this function 1, it is rather obvious how the semantics should be defined. For the function it over here, it's also rather obvious. But it's not so obvious if we have a function which is defined by recursion. And all interesting functions are defined by recursion. So if we have usual function defined by recursion, how can we then find out what should be the semantics of this function? And that's the most interesting part of the semantics. And in order to define the semantics for such recursively defined functions, we need the notion of chains. Now, intuitively, I've used the notion chain already. And chain simply means you have a number of objects in some domain, and they get more and more defined. If you recall how this looked like in these examples, we can already see some of the chains. So in these flat domains, all chains have at most length 2, because if you have a sequence of elements and elements become more and more defined, then you might have something like bottom 3, and indeed 3 is more defined than bottom, but then it's over. And in these product domains, you can have chains which are a bit longer. For example, bottom, bottom, bottom 0, and then 1, 0. So this is a chain of length 3. Elements got more and more defined, but then again, you stop. Now in these function domains, it's more interesting because here you can have infinite chains. I had an example for this already in the last lecture, and I will give you another one in a minute. But let's first define this formally. So this is the definition 219. Now we define what a chain is. So let this be an ordering on a set D. Now this you can define for any order on any set, not just for less defined or equal, and not just for domains. And then a non-empty subset of D of the form D1, D2. And it can be finite or infinite, but it can be at most countable. So of countably many arguments, countably many elements of D is called a chain. If you can order the elements, so you can say D1 is less than or equal to D2, this is less than or equal to D3, and so on. Okay, now some examples. Now if we look at, say, Z bottom, then we might have the following chains. So an example for a chain is this. Because you can order the elements, bottom is less than or equal than 3. Now obviously something like just bottom or just 3 would also be a chain. But the longest chain has length 2. This is one of the longest chains. Bottom 5, of course, is also a chain. Are chains. And the maximal length of a chain is 2. This is true for all flat domains. Now in Z bottom cross Z bottom, it's a bit more interesting. Now here we have chains, for example, like this. First element is bottom, bottom. Next element is 5, bottom. And the last element is 5, 8. Now again, this is a chain because this is less defined or equal than that, and this is less defined or equal than that. But again, chains are finite and maximal length is 3. So there are many other examples. And the maximal length is 3. And if you have Z bottom cross Z bottom cross Z bottom, you can of course also have chains of length 4. But again, finite chains only. Now let's look at function domains. How might chains look like here? Now here you can have infinite chains. And let's look at an example. And now this example is interesting also in the remainder of the lecture. So what I want to do is I want to define a chain of functions which are called fact 0, fact 1, and so on. And the reason for this name is that they are almost the factorial function. So they are approximations to the factorial function, but not quite the factorial function. So here we have fact 0, fact 1, and so on. This is an infinite chain. So here chains can also be infinite. And the idea is that fact n, each fact n, is an approximation to the factorial function fact. And it is like fact for all elements, for all arguments up to argument n, up to argument n minus 1. So fact n of x is the factorial function for x less than 1 and also for bottom, and otherwise fact n of x is undefined. So they are approximations to the factorial function, and they get better and better. So how do they look like? Now fact 0 is like the factorial function. Fact 0 is an exception to this rule. Fact 0 is undefined everywhere, but fact 1. Now fact 0 is undefined everywhere, so it's a very bad approximation. Fact 1 is already a bit better. So fact 1 is like the factorial function for all x's less than 1. Now I defined, to make things easy, I defined the factorial for negative numbers to be 1. So my factorial function is 1 for all negative numbers. So then this is like the factorial function for negative numbers and for all positive numbers less than 1. And everywhere else it is bottom. So in particular it's bottom for 1, 2, 3, 4, 5, and so on. So this is like the factorial functions for all numbers less than 1. Now fact 2 is like the factorial function for all numbers less than 2. So now I changed this 1 into 2 and this 1 into 2. That's the only difference. So it is like the factorial function if x is less than 2, otherwise it's bottom. And fact 3 is like the factorial function for all x less than 3, and so on. So this I drop at the moment. So what we can see is we can define infinitely many functions like this, and they get more and more defined. And indeed, we do have that fact n is less defined or equal than fact n plus 1. And why is this the case? Well, for those arguments where fact n is defined, fact n plus 1 is also defined, and they do the same thing. This is defined for x less than 1, and this is defined for x less than n plus 1. So this is defined on one more argument, namely on n. Everywhere else, they do the same. So fact n of x is the same as fact n plus 1 of x for all x less than 1, because it is the factorial of x, if I define factorial of negative numbers to be 1. And for n, they are different. So if I use n, then this is bottom, but for n plus 1, it is factorial of n. So they only differ on one single argument, namely on the argument n, but there fact n is less defined than fact n plus 1. and everywhere else they are the same. So indeed, fact n is less defined or equal than fact n plus 1 because they are the same almost everywhere except on argument n, and on argument n, fact n plus 1 is defined, whereas fact n was not defined. And since we have infinitely many arguments, this is an infinite chain of functions which get more and more defined, and they become more and more like the factorial function, but they never reach it. So you can already see the factorial function is a kind of limes where all these functions here converge to. Because if you go along this chain, you become more and more defined, and you become more and more like the factorial function, but there will still be, for every fact n in there, fact n is only defined for numbers smaller than n. The real factorial function is defined for all natural numbers. These approximations are not defined for all natural numbers. They stop at some point. And now how can we describe this limes where all these functions converge to? Well, this limes, the real factorial function, is the least upper bound of this chain. And I will define this on the next slide. And we will use these chains with these limites to define the semantics of recursive functions. So what is the least upper bound? Definition 2.1.10. So least upper bound. Kleinste obere Schranke in German. So if you have some order, if this is an order on a set D, and you have some subset S of D, then what does it mean if some element small d is the least upper bound of S? So an element small d out of big D is an upper bound of S if it's bigger or equal than all elements of S. So if D prime less than or equal than D for all D prime out of S. So this is what upper bound means. So it's not surprising. And least upper bound means it's the smallest upper bound. So if there is another upper bound, then this other upper bound is greater. So an element D is the least upper bound we also call it LUP for least upper bound, or it is also called supremum. If so it must be an upper bound, but moreover, we have the following thing. For all other upper bounds, E, these E's must be bigger than D. So if we have D is less than E for all other upper bounds D. And to write this in a short way, we denote the least upper bound of S by this sign. So it is like this less defined or equal relation, but turned around by 90 degrees, and then we get this. So it's the least upper bounds sign upside down. And if you have a chain, so a sequence or a set where elements become more and more defined, then the interesting question is is there a least upper bound? So do they converge until they reach some, well, to get nearer and nearer to some least upper bound? This least upper bound is the element that is approximated by all the elements in the chain. So for a chain, the least upper bound is the element that is, in some sense, approximated by the chain. Now let's look at some examples. We had chains up there. So we had this chain. One chain was this, bottom, and let's look at this, the one for Z bottom cross Z bottom. This was this one, bottom, bottom, 5 bottom, and 5, 8. Now, what is the least upper bound of this chain? So it must be an element which is bigger than all the elements, bigger or equal than all the elements in this chain, and moreover, it should be the smallest such element. 5, 8. 5, 8 is clearly the only object which is an upper bound. This is the only upper bound. Because here we compare elements by their definedness. Now 5 and 8 are already completely defined, so there is no way to get something which is bigger than 5 or bigger than 8. So this is the only upper bound, and therefore it's also the least upper bound. Now for this factorial function, it's more interesting. So let's look at upper bounds. First, let's look at arbitrary upper bounds, and then we look at the least upper bound. So what are upper bounds of this chain? Fact 0, fact 1, and so on. So these must be functions f with, how should they be defined? Now they must be an upper bound. So if f is an upper bound, then f is greater or equal than fact 0, then fact 1, then fact 2, then fact 3, and so on. Now, less defined or equals means that whenever one of these fact n's is defined, then f must be defined as well, and it must do the same thing. So, how will f look like? Now we can see that if x is less than 0, then fact 0 is undefined. Fact 1 gives us 1, fact 2 gives us 1, fact 3 gives us 1, fact 4 gives us 1, and f must be bigger. Now, in order to be bigger than 1, there is nothing bigger than 1. There's nothing which is more defined than 1. So there's just one solution. It has to be 1. Now, what happens for positive numbers? What happens if x is positive? Now, here the functions are different. Fact 0 is undefined for positive numbers. Fact 1 is defined for 0, but undefined for bigger numbers. Fact 2 is defined for 0 and 1, but undefined for bigger numbers. The next one is defined for 0, 1, and 2. The next one is defined for 0, 1, 2, and 3, and so on. So, for every x, we find a function in there which is defined on x. For every positive x, we find a function there which is defined, and it will compute the factorial of x. So if we want an upper bound, then there is no other choice than defining f of x to be the factorial of x for every x. If we would say, okay, it's defined for x until 17, but for 18 it's undefined, then this will not be an upper bound for this chain, because for factorial 18 or 19 or 20, this fact n would be defined on 18, and so f has to be defined on 18 as well. And now the remaining question is what happens for bottom. Now, in order to be an upper bound, what should f return if it's applied to bottom? Now, what do these functions return when they are applied to bottom? This fact 0, fact 1, fact 2, and so on. Let's look. So, fact 0 always returns bottom. Fact 1 returns bottom if it's applied to bottom. Fact 2 returns bottom. Fact 3 returns bottom. They all return bottom. So, all these functions return bottom if they're applied to bottom. Now, if we just look for an arbitrary upper bound, we can use anything here. Everything is bigger than bottom. So here, the value is completely arbitrary, which means that this chain has many upper bounds. All these upper bounds are identical for the integers. For the integers, they compute the factorial. For the undefined value, they can compute anything. So there are infinitely many upper bounds here. For integers, they are like the factorial function. For bottom, they can return anything. So, for example, the function which, if you apply it to an integer, it gives you the factorial, but if you apply it to bottom, it gives you 34. That's an upper bound of this chain. Now, what we will do is, we will define the semantics in this way. So if we have a recursive definition of factorial, we will build this chain, and then we say the semantics of factorial is the least upper bound of this chain. Now, the semantics should only have computable functions. In particular, should only have monotonic functions. Now, of all these f's, most of them are not monotonic. There's only one which is monotonic, namely the one which returns bottom here. The reason is, if you return something else here, then, say 34, then for bottom you would get 34, but for 0 you would get 1, and 34 is not less defined or equal than 1. So the only monotonic upper bound is the one that takes bottom here, and that's also the least upper bound. The least upper bound must be the smallest of all these f's. Now, these f's are all the same for integers. They only differ on the bottom element. And if you want to have the smallest f, then here you should take the smallest result. The smallest result is bottom. So the least upper bound of this is indeed this function, which does this, but it returns bottom if x is bottom. So the least upper bound is the factorial function. That's written on the slide as well, I think. So we now have an example where we have many, many upper bounds, but just one least upper bound. So we had this chain, fact 0, this was less defined or equal than fact 1, less defined or equal, and so on. But the whole thing is less defined or equal than this factorial function. So it is approximated. You get bigger and bigger and bigger. You never reach this factorial function, but it is the least upper bound. So this chain converges to this factorial function. Okay. Okay, to get used to this notion of least upper bounds, the following lemma might be helpful. In particular, we need this lemma later on. So we have to prove it anyway, but it also helps to get accustomed to this idea of least upper bounds. The question is, when do we have these least upper bounds? I mean, in our examples up to now, it happened that every chain had a least upper bound. But it's not so clear. Does every chain have a least upper bound? And can it be that there are many least upper bounds, not just one? Because what we want to do is we want to define the semantics of recursively defined functions as the least upper bound of such a chain. So our goal will be define the semantics of recursively defined functions like the factorial functions as the least upper bound of a suitable chain. So for example, a chain like fact 0 less than or equal than fact 1 and so on. So this would be used to define the semantics of a function, a Haskell function which computes the factorial function. And then the question is, does this least upper bound always exist? Does this least upper bound always exist? Always exist? Is it always unique? And how does it look like? Now, we will answer this question, but before we answer it completely, let's assume we know that least upper bounds might exist for a domain D. Then the question is, will it also exist for the product domain? I mean, we had these basically three kinds of domains. We had these flat base domains like Z bottom, we had product domains, and we had function domains. And the following lemma says, if we know that least upper bounds exist for a domain, then it also exists for the product domain and for the function domain, which is built from this domain. That's what this lemma says. So this says, if we know they exist for our base domains, then they also exist for our product domains and our function domains. So this says something about least upper bounds for products and functions. And in fact, it says also how the least upper bounds look like. So let us have some domains, D1 to Dn, and also domain D, and also domain D prime. And then part A says, suppose we have, now we assume that we know how to compute least upper bounds for D1, D2, and Dn, and then the question is, how do we compute least upper bounds for the product domain of D1 to Dn? So let us have a subset. S is a subset of D1 cross Dn. And the question is, how does the least upper bound of S exist, and how does it look like? And we can get this least upper bound of S by looking at the least upper bounds of certain subsets of D1, certain subsets of D2, and certain subsets of Dn. And these subsets look like this. So for all I between 1 and n, we define a set Si, and this is just the projection of S to the ith argument. So S contains tuples with n components. And Si are those values that occur in these tuples at component I. So these are the Di's where there exists a tuple D1 to Dn and containing Di in S. So for example, if we look at Z bottom cross Z bottom, and S is again bottom, 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 what did we have? 5 bottom? 5 bottom. 5 bottom and 5 8. Then S1 is the projection on the first argument. So on the first argument we have bottom, we have 5, nothing else. So this would be bottom 5, and S2 would be the projection on the second argument. And on second arguments we have bottom and 8. So that's the idea, it's just a projection. And then we have have the following properties. The least upper bound of S exists if all least upper bounds of the SIs exist. So if all these projection sets have a least upper bound, then the set of the tuples has a least upper bound as well, and vice versa. And moreover, if the least upper bound exists, then it looks like this. It is simply the tuple where the first component is the least upper bound of S1, the second is the least upper bound of S2, and so on. So now let's look whether this is true in our example. What is the least upper bound of S1? S1 is just bottom and 5. So what is the least upper bound of bottom and 5? 5. 5 is bigger than bottom, and it is bigger or equal than 5. So this is the least upper bound of S1, and the least upper bound of S2 is 8. And the least upper bound of S, indeed, is 5, 8. So this is least upper bound of S1, and this is least upper bound of S2. So indeed, we get the least upper bound of a set of tuples by computing the least upper bound of the set we would get from the first elements, first components, and the least upper bound of the second components. So computing least upper bounds can be done component-wise. That's what this lemma says. And something similar is true for functions. So for functions, now if S is be a set of functions from D to D prime, and now again, we build something like projections, but now projections means we build sets for every argument. So for all arguments I, let Si be the set. S is a set of functions. Si is the set of results that these functions would give on argument I. So this is the set of all Fi where F comes from S. So if these are functions from Z bottom to Z bottom, here S0 would be F of 0 for all these F's in S. S2 would be F of 2 for all these F's in S. S bottom would be F of bottom for all these functions F in S. And then we have something similar. So the least upper bound of this set of functions exists if all least upper bounds for these Si exist. And if it exists, then we know how it looks like. It's a function. Now this thing is a function from D to D prime. So we can apply it to any element of D. So let's apply it to element I. And how do we get the result on element I? This is the set where we have the values of all F's on the elements I. We take the least upper bound of these things. So if you look at this closely, you can see that the difference between A and B is very minor. A function is simply like a tuple, but it can be an infinite tuple. So for every element of D, we have one component. If D is Z or Z bottom, you can read this as an infinite tuple where the first component is the function value on bottom, the second one is the function value on 0, the third one is the function value on 1, the next one is function value on 2, function value on 3, and so on. And if you see this like a tuple, then part B of this lemma is identical to part A. So functions are like infinite tuples. are like possibly infinite tuples. Like possibly infinite tuples. Okay, I will prove one part of the lemma, and the other part, the proof is almost identical. Let me prove part A. So I prove A, and the proof of B is completely analogous. Now there are two directions to prove. Let me start with this one. What I want to prove here is I prove that if all, now we look at tuples. And if all the least upper bounds for the projections exist, so the least upper bounds of S1, S2, S3 until Sn, then the least upper bound of S exists as well, and it looks like required by the lemma, it's the tuple where the first component is least upper bound of S1, second one is least upper bound of S2, and so on. So what we show is if all least upper bounds of the Si exist, then the least upper bound of S exists as well, and it looks like this. It's the least upper bound of S1, least upper bound of Sn. So this is what we want to show first. Okay, so we want to show that we know that this thing exists. This is the least upper bound of S. So part 1 is let's show that it is an upper bound, and part 2 is let's show that it is the least upper bound. Show that this thing here is an upper bound of S. Okay, how do we show this? Well, we take an arbitrary element of S, and then we show that this one is bigger or equal. Okay, so let d1 to dn be an element of S. Then we know that d1 is from S1, d2 is from S2, and dn is from Sn, because these are just the projections. So di is in Si for all I. Now if di is in Si, then di is smaller than the least upper bound of Si. So di must be less than or equal than the least upper bound of Si, by definition of upper bounds. For all I. And now if d1 is smaller than the least upper bound of S1, d2 is smaller than the least upper bound of d2, and so on, then the whole tuple d1 to dn is less than or equal than this tuple by the definition of less defined or equal. This is defined component-wise. This holds if d1, if the first component here is smaller than the first component there, and the last component here is smaller than the last component here. So this is what we wanted to show. So indeed, if we take an arbitrary element of S, then this arbitrary element is less than or equal to this upper bound here. So this is really an upper bound. Now part 2 is we have to show that it is the least upper bound. So show that for all other upper bounds, show that for all other upper bounds E1 to En, that here we have that this other upper bound is bigger or equal to the upper bound that we found here. So that here we have this upper bound that we found here is less than or equal to E1 to En. Now, how can we show this? Now, if this is an upper bound of S, if we know that this is an upper bound of S, then what do we know about EI? About these components in here. E1 then must be an upper bound of S1. Why is this? Well, this E1 must be bigger than all the first, or equal, than all the first components of tuples in S. Now the first components of tuples in S, these are the elements of S1. So E1 must be bigger than all elements of S1. So EI is an upper bound of Si for all I. So if this is an upper bound of Si, then the least upper bound of Si must be smaller. So the least upper bound of Si, therefore, must be smaller than Ei, because this is the least upper bound. So Ei is an upper bound to Si, therefore the least upper bound must be smaller than Ei. And then this means, if we compare this component-wise, then the least upper bound, this tuple of least upper bounds must be smaller than E1 to En, which is what we wanted to prove. We have now shown that, indeed, every other upper bound is bigger or equal to this upper bound. So this is the least upper bound of S. So this is the first direction. Now we come to the other direction. And the other direction means now we assume that this exists. And let's say it looks like this. This is a tuple U1 to UN. And now we have to show that then the least upper bounds of S1 to Sn exist as well. And the least upper bound of S1 is U1. And the least upper bound of Sn is Un. So what we have to show is Ui is the least upper bound of Si. In other words, the least upper bound of Si is Ui. Now again, we do this in two steps. First step is that we show that Ui is an upper bound of Si, and the second step will be to show that this is the least upper bound. So, show that Ui is an upper bound of Si. Now, how do we do this? Well, let's take an arbitrary element, di from Si. Di can only be in Si. Si is the projection on the ith component. So there is some tuple where this di is on the ith position. Such a tuple is somewhere in S. That's the reason this only contains elements that were on the ith component, so there must be some tuple where this is on the ith component. And now we know that this is the least upper bound. So U1 to UN is the least upper bound of S, and therefore D1 to dn is less than or equal than this least upper bound. This is the least upper bound of S. So every element of S is smaller than this upper bound. And since we have this, we also have this. The ith component here is smaller than the ith component there. So indeed, ui is bigger than every element, bigger or equal than every element of Si. And the last step is, we have to show it's not just an upper bound, but it's the least upper bound. So, show that for all other upper bounds, bounds ei of Si, that here ui is smaller. So ui is really the smallest, the least upper bound. Okay, now if ei is an upper bound of Si, then we get the following new upper bound of S. Now this new upper bound is like the old upper bound. With this, we know that this is the least upper bound. What we do now is we replace the ith component ui by this new upper bound ei. So everything remains the same, but at position I we exchange something. And now this is still an upper bound of S. Now why is this true? Now upper bound means it must be bigger or equal than every element of S. And and this is defined component-wise. So the first component here must be bigger or equal than every first component in S. Now this holds, since this is the least upper bound. The only thing where something changed is this. So this ei must be bigger than or equal than every ith component in S. Now that holds because ei is an upper bound of Si. These are just the elements on the ith components. Okay, but if we know that this is an upper bound, and we know that this is the least upper bound, then, so u1 until un is the least upper bound, then of course we know that this ui must be smaller or equal than ei, and that's what we wanted to prove. So indeed, ui, the ith component, is not just an upper bound of Si, but it's the least upper bound of Si. Now these proofs are not too difficult and they follow the same schema. If you want to prove that something is the least upper bound, you do this in two steps. First you prove it is an upper bound, and then when you know it is an upper bound, you have to prove that it's the least upper bound, and you do this by taking another upper bound and showing that this other upper bound is bigger than your least upper bound. And that's how all these proofs work. So the proof of part B is probably a good exercise. If you understand proof of part A, then the proof of part B is very simple. Works almost the same way. Okay, so now we know that if we know how least upper bounds work for certain domains, then we can lift all this to more complicated domains. But still, for some domains, we must be sure that indeed chains have least upper bounds. That's what we really want. We want that if we start approximating functions, like we did it here with fact 0, fact 1, and fact 2, then there should always be an upper bound for every chain. And basically this is a property of the ordering. The ordering with which we compare these elements should have this property that whenever you have a sequence of increasing things, then there is something which is above all of them, and even some least upper bound. And if an ordering has this property, it is called complete. So this is the essential property which is needed for domains this essential property is completeness. And this is defined in the following definition. So now we define complete orderings. And since all orderings that we look at here are partial, it's typically called complete partial orderings. A partial ordering is simply an ordering where you may have elements that are not comparable. And our orderings are typically partial because if you remember, in Z bottom, bottom is less than 0 and bottom is less than 1, but 0 and 1 are incomparable. So that's a partial ordering. So complete partial orderings or orders, or CPO for short. So a reflexive partial order on a set Z is called complete if the following two properties hold. The first property is there must be a smallest element. So D has a smallest element, which we typically denote by bottom with index D. And the second property is that every chain has a least upper bound. Every chain S of elements of D has a least upper bound, which is also contained in D. So, with those domains that we looked at up to now, this less defined or equal relation is indeed complete. So, for those domains that we looked at up to now, those domains D that we looked at up to now, the less defined or equal relation is indeed complete. And in fact, a set is only called a domain if this less defined or equal relation is complete. Otherwise, we would not call it a domain. Now, the formal definition of domain, I never gave this formal definition, and I will not give it because it is a very technical definition. So formally, a domain is a set with a complete partial ordering like this, and some additional technical properties. And these additional technical properties are rather complicated, very complicated. Now, these additional technical properties are needed when we define data. Up to now, we just looked at predefined data structures. We had data structures like integers and booleans and so on. And we can define how the domains for these data structures look like. And if you build new data types by building tuples or by building functions, we can also say how the domains for these types look like. But of course, the user can also define types by himself. I mean, if you think of Haskell, you have the possibility to say data, and then you introduce a new data type. Now, obviously, for these new user-defined data types, you also need domains. We will say how these domains look like, but to prove that these domains will, in the end, to prove that these domains really exist, you need these additional technical properties. And this proof we will omit. So, needed to prove that dom tau also exists for user-defined data structures. So we will give the definition how dom tau looks like, but to prove that this definition is really well formed, so that this domain really exists, this proof we will not do, and therefore we will omit these technical properties. And believe me, they are rather complicated, so they would keep us busy until the end of the lecture, I would guess, and that's not what we want to do. So if you look into the course notes or on the references of the web page, there are points to the literature where you can find all this if you're interested. Okay, so we don't do this, but what we do is we will prove that for those domains that we looked at up to now, this ordering is really complete. So we will prove this for the flat domains, the product domains, and the function domains. And then we can be sure that for those domains that we look at, chains always have a least upper bound. So we can indeed later on say the semantics of a function is the least upper bound of such a chain, and we are sure that it exists. Okay, and we will do this next week.